Okay, so today we're going to talk about something called continuity. Not so much one-sided limits, but continuity is the focus. It's a pretty important topic, but it's pretty simple. We'll go over the objectives. We're going to talk about continuity. We're going to talk about one-sided limits. Now, a one-sided limit is what's the limit if the function ends? Okay, not that it goes on forever, but like if you take a semicircle, what's the limit at one end of that function? We're going to talk about the properties of continuity, what makes a function continuous, and we're going to talk about the intermediate value theorem. I think you've done this already, but even if you haven't, it's a really simple concept, okay, which involves a little bit of math. And then most importantly today, you should be a better listener for your friends and family, okay? Don't just watch somebody talk so you can wait for them to pause so you can say what you want to say. Actually listen to what they're saying. Try that. It works wonders. Okay, so continuity. What does the word continuous mean?
To not stop.
Good. Okay. So we're going to apply the KISS method to this. And I've used that term already, right? Shake your head, yes or no. KISS method. Keep it simple, stupid. Okay. So simply put, a function is continuous if you can draw it without picking up your pencil. Okay? Unfortunately, that's not a good calculus phrase to use. In other words, on the AP test, you're not going to say, this function is continuous because I drew it without picking up my pencil. But it's a good thing to have in the back of your brain when you're looking at a function to say, oh yeah, I could do that. I could draw this parabola without picking up my pencil. Or I can't draw this function because I've got an asymptote to jump over. Okay, so keep that in the back of your brain as we're moving through this lesson. Right. And I think I answered that question already. Okay, and this is what I just said. Okay, now we're going to look at some problems here. And those problems you've kind of seen already. Holes in graphs, jumps, and gaps. And there's formal names for those, but that's basically what we're looking at. In other words, if I'm drawing the graph, what is going to cause me to have to pick up my pencil? And you can already answer that question on your own, like an asymptote would cause a problem. A hole would cause a problem. Okay? Jumps in the graph, like some of the piecewise functions, would cause problems. So we're going to look at those. We're going to give them fancy schmancy names, and we're going to bring some math into this. But in general, that's what we're going to be doing. Okay? So this is important. Not only is it the definition of continuity, but it's commonly called the formal definition of continuity. So I will ask you to use the formal definition of continuity when you're explaining these problems. And this is what you'll use. And it looks very intimidating, but I'll explain it to you. There's three parts to it. In order for a function to be continuous, it has to have a value at all the points on the interval. Okay, so sometimes we'll look at the whole graph and say, oh yeah, well there's a point everywhere on that graph. Sometimes we'll just take a chunk of a graph on an interval. So let's think about something like x squared. Okay, simple parabola at the origin. That has a value at all x values. Okay. Step 2, it has to have a limit at all points. And step 3, the value from problem number 1 has to equal the value from problem number 2. If all three of those things are met, then the function is said to be continuous. Okay. To understand what makes a function continuous, it's a little bit easier to look at what will make it not continuous, or if you want to be fancy, discontinuous. Okay, so let me stop for a second. Questions so far? Drink of water. Okay, so number 1, called a removable discontinuity. You would call it a hole. Okay. The fancy term is a removable discontinuity. However, you know it as a hole. So what generates holes in a graph? We talked about that already. It's when things cancel and it generates a hole. So again, talking about it using the KISS method, I can't draw that line without picking up my pencil because I got to get over the hole there. Okay, so that's our first type of discontinuity. Questions? Okay, and we've looked at functions like this already where the x minus 1, you factor the top, the x minus 1's cancel, generates a hole in the graph. Can't draw that without picking up my pencil. Number 1. Okay. However, what I want to do is go through the 3 steps using the formal definition of continuity to show you why this doesn't work. Okay, so number 1. Does this function, and you can answer by just looking at the picture, does this function have a value at all points on the graph? No. Okay, there's a problem at x equals 1. Okay. Now we're done. As soon as you have something that violates, 1 doesn't work, discontinuous. But we'll keep going. Number 2, does it have a limit everywhere? Okay, so this is what's causing problems. So the term I use is I call that a funky point. It's a point where something funky is going on. The rest of this is fine. Limit everywhere. Is there a limit at 1?
Yes.
Yes. Okay, so we're good to go. The limit as x approaches that funky point of, what is this, f of x is equal to 1. Okay, so that one's okay. Then step 3, does the answer from part 1 and part 2 match? Well, the answer to that is no, because 1 is violated. As soon as 1 is violated, we could have stopped. Okay, does that make sense? I'll take that as a yes. That's the process you're going to go through every time when you're using the formal definition of continuity. And we'll look at it for the other examples too and show you why it's violated. Okay. This one, the whole doesn't work because it isn't defined everywhere. Okay, take a deep breath because I'm about to make it more interesting. Let's do this. Let's put a point. Let's bring that scary dot in that we saw in so many of the problems of the homework and go through the process again. Okay, number 1. First of all, I identified the funky point. The funky point is going to happen at 1. So what is f of 1? Well, in this case, f of 1 is 1. Because that's the value of the function at 1. It's where the solid dot is. Number 2, we did already. What's the limit as x approaches 1 of the function? We said that was 2. 1's good, 2's good. Now 3 is screwed up. 1 does not equal 2, and therefore discontinuous. Okay, is that sinking in a little bit? Yeah. Okay, good. So let's move on to the next type of discontinuity. Which is a jump discontinuity. Crisscross will make you jump, jump. Mac Daddy make you jump, jump. You guys know that song? Yeah, Crisscross? No? A pair of irritating pre-teenagers that had a #1 hit back in the, I guess, the early 90s. They had one hit, but their gig was they wore their clothes backwards. So they had their pants on backwards, their shirts on backwards, and they jumped around to their one-hit song. Very, very bothersome. Okay, jump discontinuity. I don't know how much I need to explain this other than the definition, or the term pretty much describes it. You have to jump on the graph. Okay. So if I move from one side to the other, change colors here to blue, if I start coming this way, I get to that point, oops, I got to jump down to this one. Okay, not good. And just like we did last time, I want to go through the 3 steps of the formal definition to see which one, to see if it works. So let me get rid of this. Oh, I shouldn't say. Not to see if it works, but to show you why it doesn't work. Okay. And by the way, I'm just going. If you have questions, don't be bashful about stopping me and asking. Better to ask than not ask. Number 1. Okay, first of all, let me ask you this question. Where's the funky point in this graph?
x equals -2.
Good. So that's where we're going to focus on -2. So is there a value at -2? What's f of -2?
2.
Perfect. Okay, good to go. That's fine. Step 2. What's the limit as x approaches -2 of the function?
There does not exist.
Beautiful. Does not exist. Now, I would then say why, or justify your answer. What would be your answer for why there's no limit there?
Left hand limit does not equal right hand.
Perfect. Okay, this doesn't work. We can stop. Done. However, number 3, yeah, it just doesn't make any sense because since 2, then 1 does not equal 2 because 2 does not exist. Discontinuous. Sometimes this will also be called the removable discontinuity. I don't know why. It's silly. For our purposes, a removable discontinuity is a whole, but occasionally you'll get some doofus call that a removable discontinuity. Okay, how we doing? Thumbs up? Questions from anybody? Something not clear? Okay. Am I going too slow? Is this too easy? Good. Okay. Third one, infinite discontinuity, also known as an asymptote. I just pointed to my butt in case you couldn't see that. Asymptote. Okay. Pretty straightforward. Let's go through the 3 points. Number 1. Okay, on this particular graph, just for giggles, Hannah, where's the funky point?
The origin.
Beautiful. Also known as 0. So, what is f of 0, Hannah?
It does not exist.
Beautiful. D, N, E. Done. We can stop there, but just for giggles, we'll keep going. What's the limit as x approaches 0 of this function?
DNE.
DNE. Okay, so this one is a complete and utter train wreck. Then number 3, 1 does not equal 2. Okay, so none of these work. This is a mess. Not continuous. And obviously, if I trace it this way, I go to negative infinity, and then I can't get back up there, so I can't trace it without picking up my pen. So it is discontinuous. Okay. That's it. Every discontinuity that we deal with fits into one of those 3 categories. And again, over and over again, you're going to come back to this formal definition. So what you want to do, what I think you would want to do in your brain is approach it logically. Okay, it's a whole, it's a, come on, Reedy. Jump or an infinite. Okay, then drop into the formal definition by doing the I, and I. Okay. Beautiful. Okay. Semicircle. Top part of a semicircle. How do we know it's the top part of the semicircle? Well, because there's a picture there, but also because it's the positive square root. Remember, we talked about taking x squared plus y squared equals 4 and solving for y to keep it a function. The positive part is the top half. The negative part is the bottom half. So let's start with that first question. What's the limit as you approach x, or as you approach -2 from the right?
Zero.
0. Yeah, it's not a trick question, it's 0. What happens when you approach from the left? Guesses?
Can't.
What's that?
You can't.
You can't, correct. DNE. There's nothing there. Therefore, it can't have a limit. So of the 3 possibilities, from the right, from the left, and at the point, only one of them works in this case. The same is true at 2. You can do 2 from the left, you can't do it from the right, and you can't do it at 2. Okay? Not a very common thing, but worth mentioning. skipping this because we knew it already. Left-hand limit matches right-hand limit. That's why it says this is really important. It answers the simple question that you will see a lot. Justify your answer. If you give DNE as an answer to a limit problem, most of the time your answer is going to be the left-hand limit does not match the right-hand limit as a justification for why it does not work. Okay. This is the fancy definition of continuity. We don't care. Let's move on. Properties. Okay. You take a continuous function, you multiply it by a number, it's still continuous. You take two continuous functions, you add them together, it's still continuous. You multiply two continuous functions, it's continuous. You divide two continuous functions. Okay, like it says, in other words, you do anything, pretty much anything to a continuous function, it's going to stay continuous. Now the big one, and this will save you a ton of trouble. That's why it's so large. Polynomials are always continuous. And I don't want to assume anything, so I'll ask, do you all know what makes a polynomial a polynomial? Yes? Is this a polynomial? Mm-hmm. Is that a polynomial? Nope. That's what's called a rational function. Okay? Polynomials are things like lines, parabolas, cubics, quartics. It's every variable is raised to an integer value, a positive integer value. Okay? Lines, parabolas, cubics, quartics, quintics, all of those other things. That's important because some of the stuff we're going to do, you're going to have to justify how certain theorems work, and in order to justify it, you're going to have to be able to establish that it's continuous. If it's a polynomial, literally all you need to say is, this function is continuous because it's a polynomial, let's move on. And if I go back to all those examples we did before, you'll notice that none of those were polynomials. We didn't look at a simple x squared because I know that that's going to be continuous. Okay, how are we doing so far? Good? All right, I see some head shaking. I'm going to, oh, look, that's how important it is. Did you see that? I'll do it again. So that's how important it is that it does the wave. Okay. Somebody's spending too much time in PowerPoint. Oh, wait, I forgot about that one too. Okay. Composite functions. I should have put this on the previous slide. Also continuous. You take a continuous function, you stick it inside a continuous function. We're still continuous. Pretty much you can't screw up continuity. Is the tangent function continuous? Bella, why not?
It has asymptotes.
Hot diggity. Boom. If we wanted to get technical, I'd push my glasses up and say, technically speaking, it has some infinite discontinuities. Where do those happen, Bella?
I don't really remember.
Ooh.
They're at...
Come on, little trig stuff. Somebody help her out. Where are the asymptotes in a tangent graph? Cool boy. Nobody remembers.
Every pi over 2.
There you go. Pi over 2, 3 pi over 2, yeah, et cetera, et cetera, et cetera. Okay, good. What about a sine graph? Is a sine graph continuous?
Yes.
Cosine graph?
Yes.
Tangent? We talked about already. Cotangent, secant, cosecant. No, no, no. Asymptote, asymptote, asymptote. Infinite discontinuity, infinite discontinuity, infinite discontinuity. Bum, bum, ba, bum, bum, ba, bum. Picture in case you didn't trust me. Okay, intermediate value theorem. Before I click on the next slide, I'm just going to explain the example that I have. The intermediate value theorem says, if you have a continuous function and you go from point A to point B, you have to hit every point in between. Now, what does that mean? Well, when Dylan was born, he was, let's say, 24 inches. He's not, Dylan, how tall are you now?
5'8".
5'8". From the point that he was born to right now, Dylan has been every height in between. And you're saying to yourself, oh yeah, he's been 4'2", he's been 4'3", but we're talking about even closer than that. He's been 4.1375 feet tall. He's been 4.3756 feet tall. Do you understand what I mean? He didn't just wake up one morning and go from 4'6" to 5 foot. It doesn't happen that way. As you grow, you cover every possible height between your starting point and your ending point. That's what the intermediate value theorem does. It only works, however, if your function is continuous. Okay? So here's the fancy schmancy definition. In my picture, I start down at 1, I end at 5, and therefore I have to hit every possible number between 1 and 5. 3.6, 4.2, 2.71857, 417, etc., etc. Okay. Does the theorem make sense, first of all, before we get into the math? Okay. And you can show a bunch of examples on how that works. Okay. But I think the growing thing is probably the best example that I have, okay, which is what I summarized in this page. So let's move on to the math now. Okay. Most commonly, IVT, the intermediate value theorem, is used to find zeros on a graph. Okay, zeros are where the function equals 0, etc., etc., etc. So you would have to establish that one of the values is positive, one of the values is negative, and if it's continuous, it's got to hit every point in between. So at some point, it's got to cross 0. We don't necessarily, with the intermediate value theorem, we don't necessarily care where it hits 0, just the fact that it does hit 0. Okay? So let's look at an example here. I've got a cubic. X cubed plus 2x minus 1. And I think that there's a 0 between the points 0 and 1. So I want to prove that there is a 0 in there. I don't care where it is, I just want to show that there is one in there. Okay, so the intermediate value theorem, if you remember back in geometry, you talked about some logic units, and we have a hypothesis, which is the first part of a sentence, and the hypothesis has to be followed. So the hypothesis for intermediate value theorem says the function has to be continuous. So in a problem like this, you have to establish that. Well, for this, it's really easy. F of x is a polynomial. We're doing okay for time, right? Yeah, okay. Polynomial. Therefore, whoops. Can't spell. Continuous. Do you all know that symbol, 3 dots? Oh, new symbol, 3 dots means therefore. Okay, so that has established that we can apply the intermediate value theorem to this particular problem. Here's my interval. Using that interval, I need to know where the function starts and where the function ends. Okay, so what's f of 0?
-1.
Good. What's f of 1?
2.
2. Okay. Now we need a summary statement. According to the intermediate value theorem, since I started with a negative value and I ended at a positive value and the function is continuous, it must hit 0 somewhere between 1 and 2. Okay. That's an S. Since f of 0 equals -1 and f of 1 equals 2, f of x must equal 0 somewhere in 0, 1. For those of you that are graphically minded, what that means is if I start down here at -1, I can't get up here to 1 without going across the x-axis because the function is continuous. Hopefully you also see that if the function isn't continuous, this won't work because I could just jump over the x-axis. But no matter how I draw this, I've got to cross the x-axis somewhere. And again, notice I don't care what the value is. I don't care where the 0 is. I just want to show that it exists. Okay, how we doing? Did all that? Yep. Oh, I wish I would remember that I did the work already. Okay, we're done. We actually were able to manage that. Two big things to come out of this lesson: the formal definition of continuity and IVT, the intermediate value theorem. There's a rule in calculus. If a function has its own, or if a theorem has its own name, it's important. So intermediate value theorem is what I call flashcard worthy. Not that all the other theorems aren't important, but again, if it has its own name, it's going to be a big deal. Okie doke.